Marina, can you tell us what you mean by a block universe?
So a block universe is a chunk of space-time in four dimensions. So three dimensions of space and one of time. So it has four dimensions instead of the three dimensions we are used to, but it's like, you can imagine it just like to be a chunk of cement, a block that's there with the four dimensions. The block has all the space of the universe, that all that there is in the universe, and also all the time, including, so it has all the past and all the future, and they are all there in that block. Imagine that you have it in front of you, the universe is there in that block. And we are inside of the universe. We are part of it, and we can't see the actual block. So in order to see the block, we would need to step outside of it. But essentially, this is the view of the block universe as a chunk of cement that has both all the past, if you want, on this corner and all the future on this corner. And in this sense, if you step outside of it, the universe is all there and it has already happened. So, but both the future and the past are there at the same time.
What do you mean by time being symmetric in a lot of accepted physics?
Yes. So physics is a very different category or a very different science to most other sciences that we know, because physicists like their equations to be time symmetric. And this means that the flow of time doesn't really exist in the equations. In other sciences like chemistry, biology, paleontology, climatology, all the equations always flow in one direction because a human being never grows young. The paleontologists discover a fossil, and it's clearly from the past. It's not from the future. The climatology, all the time is very present there. You can never evolve back because it's so complex to predict the climate that the flow of time is very important for them. But physicists like all the equations to be time symmetric. And that means that you solve an equation and you've got two solutions. For the overwhelming majority of physics, you have two solutions, even more, but one of the solution is time flowing forwards, one of the solution, time goes backwards. And then we are there with these two solutions, and we don't know a reason to choose one or the other, which one is the correct. And we look around us and we see time is moving forward, and we say, okay, that the solution where time moves backwards doesn't exist in nature, so we discard that. It's an explanation done by hand. All the equations we have in physics, we throw away half of the solutions, the one that time moves backwards, and we say that those solutions don't exist. And there is an explanation for it, but it's a very complicated and not very convincing. So physicists say time symmetry is a fundamental theory as a fundamental symmetry of nature, and most of the equations are time symmetric. And the choice which solution to choose is done by hand and has no immediate explanation.
Really? If the models that are used, the equations that are used in fundamental physics are time symmetric, what is the sort of accepted explanation for why we only experience time as going forwards?
So the explanation is by saying that when the universe began, it was in a very, 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 very special place in the space of all possible ways that the universe could have started. And it started. So we use the term of entropy that's connected to the second law of thermodynamics. Entropy is always increasing if you leave the system to evolve isolatedly. And you say, universe becoming such a special, unlikely state that it has been evolving away from that special state all the time since the Big Bang, and it's still evolving away, and we see time evolving forward because it's a reflection of that entropy increasing and having had origin in the Big Bang. And because we want to hold on to these equations that are time symmetric, then to explain why time is not symmetric, we need to ask the Big Bang to have the likelihood of 1 in 10 to the 90. And that's like having, it's much more unlikely than this, but if you are in a living room, you can imagine that the Big Bang would have been, instead of the molecules of air being spread around the living room, they are all in one corner of the living room and very, very compressed and all stacked up in a corner of the wall and not spread around. And then the Big Bang starts, and then they start spreading around in the living room. And the problem that poses for people that study cosmology like myself is then to ask, why are all the molecules in such an unlikely state, all compressed there in the corner of my living room and not spread out all over the place like it's the most likely state? What got them there? Yeah. Why? How? That's so unlikely. I'm a scientist, and I want to explain the beginning of the universe. I can't understand why the molecules are all there in a corner of the living room. And this example has much bigger likelihood than this 10 to the 90. 1 in 10 to the 90 is at 1 with 90 zeros after it is a number so small in percentage that we cannot conceive of it in our minds. That the block universe really, if we believe in the block universe, then we have to accept that there is this chunk of cement that has all the past and all the future in it. And I sometimes talk of imagining this girl, Alicia, that is stepping outside of the chunk into an extra dimension of space, like we sometimes accept in cosmology, that there may be a fifth dimension of space. And the Alicia, this girl, is stepped outside into this extra dimension, and she has the whole chunk of space-time in front of her, and she can look onto the part of the region of the past, and she could see the dinosaurs when they happened. She would see us talking right now in the present, and she could look forward and see also the future in this chunk of space-time. She would see what we're going to be doing tomorrow, and in 100 years' time, how is the future going to be? And so for this reason, the future has already happened in the block universe picture, because you could imagine stepping outside of it and seeing everything, and that means that we experience the flow of time in our day-to-day life. We have this experience of time passing, but that's an illusion. And in particular, the future has already happened. We just feel that we are going through our lives and make choices, but in reality, we're more like almost like puppets, because we are just living in a chunk of space-time that is already there and predetermined what's going to happen. The future is not open. So if we want to start answering how can we do physics if we're not comfortable with this ignoring the flow of time as a fundamental property of nature, is essentially starting to go back and propose, hold on, I'm going to say, I don't want to discard or disrespect, in a sense, the flow of time in physics. I want to say it's an important or even a deepest clue that nature is giving us to how it works. So we bring back the passage of time to fundamental theories in physics, and in particular, we are going to build the long sought after theory that unifies general relativity or gravity with quantum mechanics, and we're going to build in the passage of time already from the beginning, and the flow of time already there, and not say that time has already happened. So what me and Lee Smolin work on is theories of quantum gravity that unify gravity and quantum mechanics, where time flows forward already from these essential constituents of nature. When we describe the world with, if you want, events that are atoms of time, and the equations from the beginning, the equations that are going to solve the problem of general relativity in quantum mechanics, are from the very start, the fundamental regime of nature, are time irreversible or time asymmetric. So there is an arrow of time, not only at the thermodynamic regime, but already from the beginning in quantum gravity at the Planck scale, the very, very, very small scale of quantum gravity, where the regime of quantum gravity is important. The flow of time, the passage of time is embedded already there. So the equations we build to solve this problem have a directionality of time, and it's not a choice you do much later on at a much bigger scale to say, I throw away half of my solutions to the equations because I see time moving forward.
And so, in your model of time, your model of quantum gravity that you're working on with Lee Smolin, instead of being the sort of fundamental elements of Einstein's theory of general relativity are space-time, the curvature of space-time, and matter and energy. But whereas yours, the fundamental elements are instances of time, discrete instances of time, and energy and momentum.
Yes. So we have a model where we say that the most fundamental constituents of time are in time ticks, or we call them events. So the space-time and quantum mechanics is made up of events in time, and the events essentially are made of particles interacting, the particles that have energy and momentum. So every time an event happens. That's an interaction of particles that have energy and momentum, and that creates an instant of time. And so the model gives rise to space, time, and to some aspects of quantum mechanics by starting with this sort of atoms that are the events, these ticking or instances of time that have energy and exchange that energy. That makes up an event. They are discrete, and we have shown that we can make space-time emerge from it, and quantum mechanics arise also from it. So it's a beginning step into a theory of combining both quantum mechanics and gravity, general relativity.
So in the model that you're working on, does that mean that unlike the block universe where all the time already exists, every time particles interact, you create another instance of time? So you're creating more and more time.
Yes. So time is the fundamental quantity that you can never. That's the most basic. Almost like when you zoom very, very, very to very small scales. Everything, you stop seeing our tables and the bacteria. You continue to zoom in, and things start to look very different. But the prevailing quantity that never disappears is time. Time is always ticking in all regimes of physics in our model. So. It's like the time is something you can never get rid of. It's the most important constituent of nature.
But if you zoomed out enough to various scales, then you'd see the standard model and the apparent time symmetry, and you'd see general relativity and the apparent time symmetry there, but underlying it all is this fundamental asymmetry of time.
Yes, exactly. So the equations we start with are all time irreversible, meaning you cannot find the backwards or the reverse solution, and we've shown that from that fundamental regime where the equations are time asymmetric, you can see the time symmetric equations of something like the standard model that we need to explain. They look like they're time symmetric. We've shown that you can make emerge a regime of physics which looks almost time symmetric, which is what we see every day. Everything, the equations are almost time symmetric, and we always neglect why a little component that makes time always asymmetric. So we've shown that we can get parts of the time symmetry in the standard model arise.
And in the conference you just organised with Lee Smolin in the Perimeter Institute, you brought together a group of people who were tackling this question, both people who supported the block universe view but were interested in the questions of time, and also people like yourself who are investigating alternative models to the block universe. And what came out of your discussions? What does the future of the question of time of cosmology look like?
It was a very, very revigorating meeting, because it's such an old problem, but also more and more parts of the community are becoming aware of this problem that we have been ignoring, the flow of time, traditionally as physicists for centuries. And perhaps we have to accept or bring back time into fundamental physics to solve this problem of general relativity clashing with quantum mechanics, that the flow of time needs to be brought back into the picture, and irreversibility needs to be incorporated and taken into account if we want to solve this problem. More and more members of our community are becoming aware of this. There's also, of course, a large part of the community that thinks that the explanation of the block universe is acceptable, and the problem is that then there is no explanation for the very initial state of the Big Bang. That remains unanswered. But it was a very nice gathering of minds. We were lucky to have some of the best minds in the planet, all in the same roof, discussing the importance of time when we want to understand cosmology and quantum gravity.
So the question of time in cosmology isn't answered, but there are some of the best minds of the planet working on it. Yes.
This is a very exciting time. It's a time when more and more members are looking into explaining these very fundamental questions. It's not answered. It's a very difficult question to answer, because the small likelihood of probability of the Big Bang is so difficult. How do you explain that the universe was in such a state? And if you then start to say that's not acceptable, I'm going to build in the time asymmetry from the beginning, then you're looking at quantum gravity and looking at for the answer in quantum gravity, which is something that we are working very hard on and hope to solve. But it's a work of many decades. So.
Brilliant.